Okay, morning everybody. Today's class is going to be on multiplier. So starts the main topic here. This is an sequential multiplier. So if you see in the multiplication, okay, if you carefully examine what is being done in multiplication is, okay, this is the number, right? This is being multiplied with another number, another binary bit. So if it is 1, what are we doing? If it is 1, we are just copying this number below here, right, as it is. If it is 1, we are just copying the number as it is. And then what are we going to do? We are going to put the next, okay, towards the left, okay, or I can say in another way, I am going to move this towards the right, okay, and then I take the next number, next bit. Here if it is 0, I am going to put all zeros here, right? I am not going to do anything, and then I am going to move. So I'm going to add these two things and then move the entire thing towards the right, okay. And again, if it is a 0, these are all zeros out here, right? So if it is a 0, I am not going to add anything, okay. I am just going to just shift the data towards the right. And if it is a 1, if you see the last, there is a 1, so I am again reproducing this whole thing and adding to the previous data. So what we are actually doing in a multiplication is, in a binary multiplication, if it is 1, okay, we are copying the same, okay, this number down, and then after copying it, for the before the next operation, we are shifting it to the right. Then if it is a 0, we are not doing anything, we are just putting a 0 here. And then again, if you have a 0, we are just putting it, putting a 0, shifting it right. If it is a 0, you put a 0, shift it right. If it is a 1, put this number back here and shift, and then you are adding it, okay. So this is how a sequential multiplier is being done. So this thing can be implemented in a hardware in a very simple manner. So once you see the hardware, you will understand how a multiplier works. So here what we are going to do is, initially in the accumulator, this is an accumulator, right? This is, we are going to put all zeros here. We are going to put all zeros here. Here we are going to put q, the number which we are going to multiply. This q is this number, okay, this one, okay, this number we are going to put it here, right? And this number what we are going to multiply with is going to put here as a multiplicand in one more register. So this is a register, this is a register, right? So this is another accumulator, this is also a register, okay. This is if it is 4-bit, this will also be a 4-bit. This is the 5th bit which caters for the carry, okay, for coming from this stage, okay. So this is one register, this is one register, this is a third register, this is an mux, okay. Now what we are doing is, initially this is all 0, okay, this is all zeros here, and this is also all accumulator is also a 0 here. No, here multiplicand, you have put the multiplicand, it is all 0. Now suppose here we have the multiplier. If the first bit of the multiplier is 0, what do we do? Then what, this control signal, okay, it will give a 0 out here, okay. We are just sensing the last rightmost bit of the multiplier, it will sense a 0 here. Once it is 0, this is the mux. So mux will add a 0. So this is 0 here. Accumulator, already we are initializing it with a 0. So the 0 will get added out here, and it will be available here, right? So during the positive going edge of the clock, so this data will be loaded into this, okay. It will be loaded into this register. So whatever is being added here, so 0 0 0 0 will come here, carry also will be 0 here, right? And suppose instead of 0, it were 1 here, suppose it was a 1 out here, okay. So you have 1 available here. So if it is a 1 available here, okay, the mux will take multiplicand, it will take the multiplicand and it will add the accumulator. Accumulator was 0 here, so the first multiplicand will get added here 0, and then that multiplicand will be available out here. So during the next positive edge of the clock, so it will be available here, okay. After this 0, it will be available here, and during the positive edge of the clock, that will get loaded out here into this register. So is this first step how it is being implemented? Is it understood? What we are doing is, if it is a 0, okay, this is all going to be zeros here. If it is a 1, this is the same thing is going to be put back here, here. So that much implementation is done in the first step. Okay, you have put all zeros out here, right? You have put this number, this number out here. Okay, so it will sense the last number, right? If it is a 0, then I am going to add a 0 here. So 0 0, it will remain 0 here, all these accumulators. But if it were 1 out here, then this multiplicand will get into the adder, so that will come out here. Okay, now after doing this first step, what is the next step? You have to shift it to the right. Okay, so you have an control signal. So once the addition is over, say we are doing it load in the positive edge, in the negative edge what we need to do is shift it to the right. Okay, so the entire data will get shifted to the right. So whatever data was available here, right, it has gone shifted to here. So once we have used this data, okay, this has become irrelevant, right? This has become irrelevant. So what we do is so we are throwing it out from here and pushing this data here. So the next bit which is available here, this, okay, that comes here, right? So now you are going to again check whether it is going to be a 0 or it is going to be a 1. If it is a 1, you are going to add it again. If it is a 0, you add 0, right? So you add 0. If it is a 1, you are going to add multiplicand if this last bit. And if it is a 0, you are going to if it is a 0, you are going to add 0. If it is a 1, you are going to add the multiplicand. Okay, again you are going to load that data here during the positive edge of the clock. In the negative edge of the time, you are going to push it towards the right. So in the third cycle, you will find here, now the third bit is going to be coming here. Likewise, in the fourth cycle, all the 4 bits would have been sensed and necessary action would have been taken, whether it is to be added with the multiplicand or with the 0 in the 4 cycles. So okay, another things which happens here at the end of the 4 cycles, okay, this entire product, okay, this product will be available from here to here, because that is being pushed out. So this multiplier information, whatever was earlier, is also not available now. This is known as the accumulator. Okay, this is known as the accumulator. From here to here to till here, okay, all the 8 bits and plus this 9th bit will have the final result here like this. Okay, so that is the end of the 4th cycle. This everything will be available here. So multiplicand will continue to remain there. Okay, so is this thing clear to all of you? Have you got a rough idea how things work?
Sir, please explain again.
Yeah, okay. So let me take an see, initially I am going to put 1 0 0 0 0. Okay, let me put that 1 0 0 0 0 out here. Right here it is going to be 1 0 0 0 0, and then I am going to put 1 0 0 0 1 here, 1 0 0 0 1 here, and here I am going to put all zeros. Okay, it is going to be all zeros out here. So now what happens is the last digit is 1 out here. Okay, so this one is coming here, so this will give an 1 output here. If it is giving a 1 output here, so what happens is whatever data was available here, this is 0 initially, so here it is the sum of 0 and multiplicand, so that sum is available here. So this is a register. So in the first, so this data, okay, is 1 0 0 0 is available here, output of the n bit. That is the initial condition. Okay, there is no clock here. Okay, have you understood till here, all of you?
Yes, sir.
Okay, in the accumulator initially it is all 0 0 0 0. Here what is the data available? It is 1 0 0 0 1 0 0 1. We have put 1 0 0 1. So that one is available here. Since that one is available here, this is the multiplicand. Okay, multiplicand is 1 1 0 0 0. So that is available here. So this is available. So this n bit adder, so this will add these two, so that 8 is available here, right? During the positive edge of the clock, okay, this data will get loaded into positive edge of the clock means the data will get loaded into this register. So this register after the positive edge will become 1000. It will become 1000, right? So the final result answer what I have 1000 here, and this is going to be 1001 here. This data is available here. Okay, in the negative edge of the clock, this particular data is going to be shifted right. Okay, from here the last bit will come here, this will be the last bit will be thrown out from here, right? So this one is going to be thrown out, and here it will become 100, and from here the last bit which was 0 here, that would come here, right? Is it okay till here to all of you?
Yes.
Okay, now in the next positive, now this 0 is available here now the second time, so now it will sense a 0, so it will add a 0 here. That means I have shifted this. Now in the next step I am going to add a 0, because it is 0 here, it has sensed a 0, so I am going to add zeros here, right? So this will have a 0, this will have the previous data itself, so that is not going to change here, because whatever is the accumulator, so it is, I am adding a 0 in fact here, so that 0 is available, the previous data, so this data will not change because I am going to add a 0. So in the next load condition the same data will get loaded here, it will not make any change. Okay, so in the negative going edge of the clock. Okay, so in the negative positive going edge of the clock, in the negative going edge again this will be shifted, pushed to the right. Okay, so at the end of the 4 cycles what will happen is the product will be from here to here, you will get the product from here to here, and this whole thing will represent the product. This will still have the multiplicand. Is it okay? At the end of the 4 cycles what would happen?
So, we don't need multiplicand after the first cycle.
No, multiplicand will be required, because each cycle it will keep checking whether it is 0 or 1. Multiplicand will always be required.
But we are directly adding it to the previous.
No, whether to add multiplicand or we have to add the multiplicand or 0, that will be decided by the mux, and that will be decided by the last bit here.
So if in the multiplier we have 1, then we will be adding multiplicand, or else we will be adding a 0.
Yeah, correct. In the multiplier only the last bit, remember, only the last bit Q0.
Yes.
Okay. So I am sure you have grasped only 50% of it. Okay, now we'll see an example. After that we will revisit this. Okay, so I'll not discuss this flowchart also. You can correlate this flowchart and this diagram later on, okay, as a home assignment. But what I'm going to do is I'm going to give you an example which will clear. So suppose I have to do 3 into 5, right? So this accumulator is, I have put a 5-bit accumulator here. Okay, 5-bit includes this carry. Okay, includes this carry, because when you add two 4-bit numbers, it will be a 5-bit, the output will be a 5-bit number. So this I've just clubbed it as a 5-bit number. So this is the A, this is 5, right? 3, this is 5, you are going to multiply it with 5. This is 3, this is A, this is 5. Is this first line clear to all of you? You will get yeah, this is important for your comprehensive exam also. So if you have doubt, then I'll repeat it 10 times, no problem. But is the initial condition clear to all of you? We have put 0 out here, right? We have put 5 here and 3 here in MAQ. Is it okay with all of you? And if I go yeah, this is M, this is
03.
Yeah.
So why MAQ initial values? I mean,
Initial condition, is it? No, we have to.
Yes, sir.
We have to tell now what to multiply. So we have to load that initial value into A, 3, and 5, and then in 4 clock cycles you have to get a result of 15. Is it okay?
Yes, sir, I got it. But in case in case we multiply more than 5, so we'll get an overflow, right? How will we account for the overflow?
Okay, don't worry about overflow things and all right now. We'll understand the concept. So obviously there will be overflow detection and the number of bits and all. Okay, that like in adder we had, so something similar we'll have here. Okay, we'll just try to understand the working of a multiplier. Okay, other contingencies we'll tackle later on. Okay, the first initial condition is understood to everybody.
Yes, sir.
Okay, now during the positive edge of the clock, okay, what is q last is 1. Okay, right, q is 1. So if I go back to the figure, I'll keep although it might be slightly irritating, I'll keep going back to this diagram. Okay, so if q is 1, what is going to be the output of the adder? It is going to be multiplicand, right? For the first one, whatever was the multiplicand, that will be available here. And I told during the positive edge, this a will be the data whatever was available out of the adder will be stored into the accumulator. Now if I go back here, during the positive edge of the clock, okay, whatever was the data available at m has got loaded onto a. Okay, whereas q, there is nothing happening in q. There is no loading here, only the loading is happening in a. So q remains like that. M also, there is nothing happening in m. Okay, m also is a fixed register. Q also is nothing happening in q. So only in a, because you had initially a 0, now since it is m, you are adding a plus m, so this has become a plus m now. So is this clear to all of you? The second line, how it has come?
Yes, sir.
Anybody? If you has got a doubt, then I'll let. Okay, now after having done that, say in the negative edge of the clock, we are going to shift the data to right. Okay, now what are we shifting? If I go back to I am shifting between a and q. Okay, m, no shifting is happening in m, between a and q. Okay, so between a and q, I am going to shift this data here in the negative edge of the clock. So what is happening is, so 0 0 1 1, this is going to remain here. Okay, now I am going to shift it. So whenever I am going to shift, I am going to put a 0 here. This is 0. Now 1 2 3 4 zeros. This one has come here. Now 0 1 0. This one which was earlier there, that has been pushed out. Okay, now this is a 0 available here. For the next operation, the last bit is 0. Is this clear? Shift right operation to all of you. Is it clear? Can somebody say yes or no so that I know?
So basically the LSB of the main or the LSB of A got shifted to the MSB of the Q, and
correct,
everything shifted.
Correct. Right, from here we have pumped in 1 0 and we have thrown away the last bit here. Now it is a 0 out here. Since it is a 0 out here, okay, now I am going to see what happens in the floor. It's a, here I have a and here I have 0. Right, because from the control, this is the last bit is 0 here. So a plus 0 is going to be a here. So I am going to reload again in the positive edge of clock. Here it is a available. Again a itself will get loaded here. So if I go back here, during the positive edge of the clock, again this a itself, there is no modification of a here. A itself gets loaded here. Is the second this operation, this for the second positive edge of the clock, the operation is clear to all of you?
Yes, sir. Yes.
Okay. Okay. Now I am going to shift it right. Okay. Now so m remains here. Here if this one is going to come here, this 1 0 is this one here. Okay. Now I have a 1 available here. Right, now since it is 1 here, in the next positive edge of the clock, this is going to be a plus m, right? Because if you go back here, okay, here if it is 1 here, it will, a was available here again m is also here, so a plus m will get loaded here. So now if I have here in the positive edge of the clock here, okay, what was the accumulator was this, right, plus m, this a plus m. If you see this diagonal, this gets added here, so this is the new data which is going to come into the m, right? Now I am going to have in the negative edge, I am going to again shift it right again here. So this one comes here, this one comes here, this one comes 0. Since it is a 0 here, okay, in the next fourth operation nothing is going to happen. So I am going to put 0 0 0 0 here, 1 here, right? This is going to remain out here. Again in the negative edge of the clock, this data is being, okay, pushed towards the right. So it is 0 0 0 0 0 here. So if you see, what is this? This is 15, right? And end of the 4 cycle, what I got, the information what I got is 15. Is it clear to all of you how this works?
Sir, how will it know when to stop?
Because the number of bits, if it is a 4-bit processor, it will give 4 clocks, right? Okay, is it okay?
Sir, but like how will we physically tell it has to stop? Like, is there another mechanism for it?
Yeah. See the microprocessor is a complex. It will have a control sequencer. Once this data, that once we will learn about microprocessors, we'll see depending on the instructions. Once we give an instruction, each instruction, it is known that, say, for an add operation these many clock cycles are required, for a divide operation these many operations are required, for just to move one data from place A to place B these many clock cycles. They are all known to the microprocessor. So once we tell the microprocessor some command, so it will automatically know how many clock cycles are required. Okay, so it will do accordingly. Is it okay?
Excuse me, sir.
Yeah, tell me.
So, two doubts here, sir.
Yeah.
So, first of all, the size of register A should be n plus 1. I mean, if it's an n-bit
Yeah.
multiplier.
Yeah, correct.
Because
That will
one
be
bit of carry.
Carry will be there. Yeah.
Yes. So, and second thing, we are using a mux here, but when we give a 0, then all the outputs should be 0. But if we give the mux an output, an input 1 over here from the control sequencer,
Yeah.
how will it load a n-bit data into the n-bit adder, sir, with just one input?
No, that 0 is a 4-bit data. 0 0 0 0.
Okay. Okay. So we are giving it a 4.
Yeah, 4 zeros, 4 zeros.
And similarly, when we are giving it a 1 also, we'll give it a 4-bit 1.
Yeah, 4. No, when we give it a 1, not 4-bit 1, the multiplicand data will be given here.
Yes, sir. So the multiplicand is an 4-bit data in this case,
Correct.
and the mux has to sequentially load those 4 bits into the n-bit adder.
Not
Is that
sequentially,
what-
all the parallelly 4-bit output will be available there. Mux can have two 4-bit inputs and one 4-bit output.
Okay, yeah. So it's a 4-bit mux in total.
4-bit mux. Okay, 4-bit mux.
Okay, and sir, also
Good thing you brought it out, because this many people might have the similar doubt. Okay, it's a 4-bit mux. Yeah.
Sir, can you just take a small example of how we would cater for the carry, sir? Because it's getting added to the left of the whatever the sum comes after we add the multiplicand, right?
Yeah.
So if it's getting added onto the left, then it would become a part of the A value in the next cycle.
Correct. No.
Okay.
When it's being loaded. Okay. You meant to say, okay. So that is becoming in part of the next circle. It doesn't matter. It will still work. Okay. It doesn't matter.
Okay, sir.
Doesn't
All
matter.
right, sir.
Yeah. So that will be pushed. Right. Okay. So I have one more example out here. 5 into 6. Right. So I have let's go through this also, so that you are absolutely clear about this, how the multiplication works. Okay, this flowchart also we can discuss. The multiplicand B multiplier is in Q. Then if A is equal to 0, the same thing, whatever we discussed here, okay, that is written. Okay, so this is more for the computer science students who are you will have to make flowcharts everywhere. For chaps like me, I straight away jump into the circuit implementation. Okay, so this is and a flow chart. Okay, qn, if it is last, if it is 1, if it is 0, just shift right. If it is 1, and then the accumulator is a plus b, the same thing, and whatever we discussed is shown in the form of a flow chart here. Okay, now if I take a second example of 5 into 6. Okay, so here 5 is loaded here, 6 is loaded here, accumulator is 0. First clock cycle, this is 0. The first is 0, so the accumulator comes straight away, so there's nothing is being added, so 0 0 0 here. This is also going to be following here. Okay, in the negative edge of the clock it is going to be shifted right. Okay, so these are all zeros, as such it doesn't make any difference, so these 1 1 will come here, 1 1 here. So in the next clock cycle, since this is 1 here, it is going to be, accumulator is going to be added. So what is this? This is actually sum of these two. Okay, you can see this horizontally also, this plus this comes here, right? So it is coming here as such. Okay, so this gets reflected, this doesn't get changed during the add operation, this is going to change only during the shift operation, right? So here it's an add operation, so this is going to get reflected as it is. Now after that, once we have done that, we are going to shift it again, right? So this remains same, shift, so this 1 0, this 1 is going to be pushed here, 0 0, this last one is going to be thrown out, so this is 1 is available here. Since it's 1 is available here, you go to add it. Now again we are going to add these two, this and this, right? If you add it, you get 0 0 1 1 1 here. This is, since it's an add operation here, nothing is going to happen here, so this is going to come here. Again in the shift operation, this is going to move here, so you have one more 0 which is coming here, you have 1 1 1 1 0 0 here. Okay, in the last fourth cycle, again since it is a 0 here, we are just going to we are going to add 0 only, so this accumulator data is going to come as it is down. So this is going to be during the positive edge of the clock, this data is going to be, and here it is in a load operation, so this is going to get reflected as it is. And then in the last shift operation here, this is going to be shifted. Here you have one more 0 coming here, and this last 0 is going to be thrown out. You have 0 here, this one coming from the accumulator to the queue, you here. So this entire thing is product. Now if you see, this amounts to 30, whatever is, this is 30, 5 into 6. Okay, so you can expect these kind of questions in your final exam also. Okay, so today I am supposed to take a feedback, so I'll stop it here. In the next class, what we are going to learn is a Booth algorithm. Okay, so this algorithm, mind you, is only for unsigned numbers. Okay, this will not if you are going to multiply a positive number and a negative number, so you have to just keep that last signed bit. Now if it is a normal signed bit, then you have to keep that signed bit separately, do the multiplication, and subsequently put back the sign number. If it is 2 positive, you put a 0, or so if it is a 1 and a 0, 2 ones, then you have to put a 0. So you can do an XOR operation and restore the sign bit. Okay, but this will not work for 2's complement and all. This whatever we studied here today was for simple unsigned numbers. Is it clear to all of you? Okay, it is only. Whereas in the next class we are going to learn about Booth algorithm that will handle even the 2's complement multiplication also. So that's a big topic, so I don't want to start it now. It will require more than half an hour to 1 hour to explain you the Booth's algorithm. So that's all for today. Is there any doubts with regards to today's class? No? So let me stop it here.